Welcome back. Let's start with this example. We have the integral of 20 to the power of x dx. And so when you have an exponential function where the base is a value other than e, you're going to want to use this integration rule right here. We have that the integral of a to the power of x dx, where a is a positive real number, is equal to 1 divided by the natural log of that base a times a to the power of x, and then plus c. All right, and so for this example right here, our base is 20, right? So a is equal to 20, and so we will have that this is equal to 1 divided by the natural log of 20 times a to the power of x, or in this case, 20 to the power of x. And so we have 20 to the power of x, and then plus c. And so then we can simplify and have that this is equal to 20 to the power of x divided by the natural log of 20 plus c. And that is the final answer, or the solution, to this integral. Next, we have the integral of 9 to the power of 4x dx. And so how are we going to solve this integral? Right, last time we just had 20 to the power of x, but in this case, this exponential function has a power that is not just x, it is 4x. And so what you're going to find is that when you have an integral of an exponential function where that power of the exponential function is not just x, you're going to want to use u-substitution and a variation of that integration rule, right? So here we have the integral of a to the power of u du is equal to 1 divided by the natural log of a times a to the power of u plus c. And so if we set u equal to 4x, we will have that u is equal to 4x, and then we're going to want to take the derivative of that. So we will have du dx is equal to 4, right? The derivative of x to the first power is just going to be equal to its coefficient, which in this case is 4. And then we'll solve for du by multiplying both sides by dx. And so we'll have that du is equal to 4dx. Now, when you use u-substitution, you want whatever du is equal to be found inside your integral. Now, in this case, I don't see a 4dx in this integral, but I do see dx. And so if we divide both sides by 4, we'll have du divided by 4 is equal to dx. And now we have a term of du that is equal to something that we can find in our integral and therefore replace with that du term so that our integral can be rewritten entirely in terms of u. And so we can do that now. We can rewrite this integral and have that it is equal to the integral of 9 to the power of u times du divided by 4, right? We replaced 4x with u because that's what we set it equal to. And then we replaced dx with du divided by 4 because that's what we set that equal to. And so if we pull this 1/4 to the outside of the integral, we'll have that this is equal to 1/4 times the integral of 9 to the power of u du. And now we can use this integration rule, and we will have that this is equal to 1/4 times 1 divided by the natural log of the base, which is 9, times 9 to the power of u plus c. And so now our last step is to replace u with what we set it equal to. And so we'll have that this is equal to 9 to the power of 4x divided by 4 times the natural log of 9. And then don't forget to add c. Okay, and so that is the answer to this integral. All right, so next we have the integral of e to the power of x times 3 to the power of e to the power of x dx. And so how do you think we are going to solve this integral? Well, for one thing, we're probably going to want to use u-substitution because we see that we have 3 to the power of some function that is not just x, right? So when you see that, you most likely are going to want to set whatever that power is equal to u. Now, that's not going to be true for all cases, but in the majority of integrals where you have an exponential function, that is going to be the case. But remember, when you use u-substitution, whatever you set equal to u, you want to make sure that that function's derivative is also found within the integral. And so in this case, if we're going to set u equal to e to the power of x, what is the derivative of e to the power of x? Well, it's actually one of the simplest derivatives. The derivative of e to the power of x is just e to the power of x. And so do we see that function in this integral elsewhere besides that exponent? Well, the answer is yes, because we see it right here. And so we should be able to set u equal to e to the power of x, and u-substitution will work just fine. And so let's try this out. Let's set u equal to e to the power of x. And then if we take the derivative, we will have du dx is equal to e to the power of x. And then let's multiply both sides by dx to solve for du. And so we'll have that du is equal to e to the power of x dx. And now let's check to make sure that what du is equal to can be found in our integral. And so it should work out because we checked that beforehand, but we have e to the power of x dx, and in our integral we have e to the power of x dx. All right, and so now we can rewrite this integral to be completely in terms of u. And so we'll have that this is equal to the integral of 3 to the power of u du. Right, we changed e to the power of x to u because that's what we set it equal to. So we have 3 to the power of u. And then we replaced e to the power of x dx with du because that's what we found that that was equal to. Okay, and so then we can use our integration rule, and we'll have that this is equal to 1 divided by the natural log of the base, which is 3 in this case, times that function in the integral. So we'll have 3 to the power of u plus c. And so now we have one more step, and that's just to replace u with what we set it equal to, which is e to the power of x. And so our final answer is that this is equal to 3 to the power of e to the power of x divided by the natural log of 3 plus c. And that is the solution to this integral, which would also be the antiderivative of this function. Up next, we have the integral of 5 to the power of the natural log function divided by 2x times dx. And so how do you think we are going to integrate this function? Well, the first thing that I'm going to want to do to simplify this a little bit is pull out the constant multiple of 1/2 here, right? We have 1 divided by 2 that we can pull out in front of the integral. And so I'll do that. This will be equal to 1/2 times the integral of 5 to the power of the natural log function divided by x dx. And so now that we have rewritten our integral here, I see that we have an exponential function of 5 to the power of the natural log of x. And so now remember, when you see that you have an exponential function where the power is a function other than just x, in this case it's the natural log of x, you are probably going to want to set that function equal to u and use u-substitution. And so remember, when you do that, you want to make sure that whatever you set equal to u, the derivative of that function is also within your integral. And so if we're going to set u equal to the exponent here, what is the derivative of the natural log of x? Well, we know that the derivative, d dx, of the natural log of x is equal to 1 divided by x. And so do you see this function in this integral here? Well, maybe you don't see it right away, but we could rewrite this integral to be equal to 1/2 times the integral of 5 to the power of the natural log function times 1 divided by x dx. Right? If we were to multiply these two functions together, we would have this function right here. And so the derivative of the natural log function is in our integral here. And so u-substitution is going to work here if we set u equal to the natural log of x. And so if we clean up our work here, let's set u equal to the natural log of x, and that will mean that du dx is equal to 1 divided by x. And then if we multiply both sides by dx in order to solve for du, we will have that du is equal to 1 divided by x dx. Okay, and so then just to be sure, let's just check one more time that whatever du is equal to is found in our integral. And so if we look at our integral, I see that we have 1 divided by x times dx, which is what is equal to du. All right, and so then we can rewrite this integral in terms of u, and so we will have that this is equal to 1/2 times the integral of 5 to the power of u times du. Right, we replaced the natural log of x with u because that's what we set it equal to, and we replaced 1 divided by x dx with du because that's what we found that that was equal to. And so now we can use our integration rule, and so this will be equal to 1/2 times 1 divided by the natural log of the base, which is 5, times 5 to the power of u, right? Whatever is in our integral, we multiply it by that, and then we add c, our constant of integration. All right, and so then if we simplify by multiplying our expressions together and changing u back to what we set it equal to, the natural log of x, we will get our final answer. And so if I clean up my work here, we will have that this is equal to 5 to the power of the natural log function divided by 2 times the natural log of 5 plus c. And that is the solution to this integral. All right, so here we have the integral of the quantity 2 minus x times 4 to the power of the quantity 2 minus x squared times dx. And so this looks like a very complicated integral, but just like with our previous examples, if you see that you have an exponential function where that power is a function other than x, you should try using u-substitution by setting that function equal to u. Just make sure that you can find that function's derivative somewhere else in this integral. Right, so if we were to set this exponent of 2 minus x quantity squared equal to u, would the derivative of this function be found in this integral? Well, let's find out. Let's just set u equal to that exponent. We have 2 minus x to the power of 2. And so if we take the derivative of this function, du dx, we will need to use the chain rule because we have a composite function, right? We have this function inside a quantity squared. And so we'll start by taking the derivative of the outside function. And so we'll multiply 2 down, right? So we're going to have 2 times that same inside function of 2 minus x, and then that will be to the power of 2 minus 1. And then we need to multiply by the derivative of the inside function. Now the derivative of 2 is 0 because 2 is a constant, but the derivative of negative x will be negative 1 because the derivative of x to the first power is equal to its coefficient, which is negative 1. And so we'll multiply by negative 1. Okay, and so if we simplify, du dx will be equal to negative 2 times 2 minus x to the power of 1. But we don't need to write the power of 1, so I'll just erase that. And this is the derivative of this function. All right, and so now that we have the derivative, let's just see, is this derivative found within this integral? So we're looking for negative 2 times the quantity 2 minus x. And so if we go to our integral here, I see that we do have the quantity of 2 minus x in our integral. And so even though we don't see this negative 2 in there, we do see the most important part, which is the part that has our variable of x in it. And so we do have a match here. We can find this function's derivative in our integral, and so the u-substitution is going to work here. All we have to do to finish it off is to solve for du and make sure that what is on this side of the equation can be found in our integral. And so let's finish this up. Let's multiply both sides by dx and solve for du. So we'll have du is equal to negative 2 times 2 minus x dx. And then remember what we saw, this negative 2 cannot be found in our integral, and so let's just divide both sides by negative 2. And so we'll have that du divided by negative 2 is equal to 2 minus x times dx. And now we have a term of du that is equal to something that we can find in our integral, right? The quantity 2 minus x times dx is in our integral, okay? And so now we can rewrite this integral in terms of u. So we will have that this is equal to the integral of 4 to the power of u times du divided by negative 2. Right, we replace the exponent here with u because that's what we set it equal to. So we have 4 to the power of u, and then we replaced 2 minus x dx with du divided by negative 2 because that's what we found that that was equal to. And so now if we pull this negative 1/2 out to the front, we'll have that this is equal to negative 1/2 times the integral of 4 to the power of u du. We can now use our integration rule for an exponential function that has a base other than e. And so if we clean up our work here, we will have that this is equal to negative 1/2 times 1 divided by the natural log of our base, which is 4 in this case, times that function in the integral, 4 to the power of u, plus c. And so then we just need to replace u with what we set it equal to. We have 2 minus x quantity squared. And so if we simplify, this will be equal to negative 4 to the power of 2 minus x squared divided by 2 times the natural log of 4 plus c. And that is the final answer, or the solution, to this integral for this example. All right, so for our last example, we have the integral of 7 to the power of 6x divided by 1 plus 7 to the power of 6x times dx. And so how do you think we are going to go about solving this integral? Maybe you're thinking we should set u equal to the exponent of this exponential function because it's not just x, right? That's kind of what I've been telling you this whole video. However, that's actually not going to work in this case because we have another exponential function as part of our denominator. And so if we set u equal to 6x, that's really not going to make this function any simpler to integrate. It's not going to get it in a form that we know how to integrate. And so we're probably still going to want to use u-substitution to make this integral easier, but we're not going to want to set u equal to the exponent. And so what are we going to want to set it equal to then? Well, what if we set u equal to the numerator or the denominator of this function? Well, we would have to take the derivative of an exponential function with a base other than e either way. And so if we remember that derivative rule, we know that the derivative ddx of some exponential function with a base of a, where a is a real positive number, to the power of u, where u is some function of x, that is equal to a to the power of u times the natural log of a times the derivative of u with respect to x. And so notice that the derivative of that exponential function a to the power of u includes that function a to the power of u within it. And so if we were to take the derivative of one of these two exponential functions, notice that the derivative would include that same function. And so if we're going to use u-substitution and we ask ourselves that question, do we see a function and its derivative in this integral? The answer is yes, because an exponential function like 7 to the power of 6x is going to have that same function within its derivative. And so in this case, we're going to want to set 1 plus 7 to the power of 6x equal to u, because the derivative of 1 is 0, and then added to the derivative of this exponential function will match up with what we have in the numerator. And so if we do that, if we set u equal to 1 plus 7 to the power of 6x, then du dx will be equal to the derivative of 1, which we set is 0 because 1 is a constant, plus the derivative of 7 to the power of 6x, which if we follow this derivative rule, will be 7 to the power of 6x times the natural log of 7, that base, times the derivative of the exponent, or in this case, 6x. And the derivative of 6x is just 6 because the derivative of x to the first power is just equal to its coefficient, which in this case is 6. And so if we solve for du here by multiplying both sides by dx, we will have that du is equal to 7 to the power of 6x times the natural log of 7 times 6 times dx. Okay, and so then we want to check to make sure that whatever du is equal to can be found within our integral. And so I see that we have 7 to the power of 6x dx in our integral, which we also have here and here, but I do not see the natural log of 7 or 6 in this integral. And so, since these are just constant multiples, right, they're not defined with x, we can just divide both sides by those, and then we'll have a term of du that will be equal to what we can find in our integral. And so if we do that, we'll have that du divided by the natural log of 7 times 6 is equal to 7 to the power of 6x times dx. And so now we have a term of du that can replace something that is found in our integral. And so now we can rewrite this integral in terms of u. We will have that this is equal to the integral of 1 divided by u times du divided by the natural log of 7 times 6. Right, we replaced 1 plus 7 to the power of 6x with u because that's what we set it equal to. So we have 1 divided by u. And then we replaced 7 to the power of 6x dx with this term of du, which is what we have right here, because that's what we found that that was equal to. Okay, and so then if we pull out 1 divided by the natural log of 7 times 6 to the outside of the integral, this will be equal to 1 divided by the natural log of 7 times 6 times the integral of 1 divided by u du. And so now we have an integral that we know how to integrate using an integration rule, that the integral of 1 divided by u du is equal to the natural log of the absolute value of u plus c. Right, this is the log rule of integration that we can use to integrate a rational function like 1 divided by u. And so if we clean up our work here, we will have that this is equal to 1 divided by the natural log of 7 times 6 times the natural log of the absolute value of u plus c. And so now all that's left to do is to replace u with what we set it equal to. And so our final answer is that this is equal to 1 divided by the natural log of 7 times 6 times the natural log of the absolute value of 1 plus 7 to the power of 6 times x plus c. All right, and so then this is the final answer to this integral. All right, and so that is all I had for this examples video. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.